Hello, everyone, and thank you for attending today's webinar, A Case Study in Energy Storage. I'm Kelly Pickerel, editor with Solar Power World. Before we begin, we want to let you know of a few things. This webinar will be sent to all registrants, so you can view it again. Slides are available to view at any time in the resource widget at the bottom of your screen. You can submit any questions related to today's webinar in the Q&A widget. We will try to answer these during the webcast. If we do not get to your question, our presenters may reach out to you after. And finally, if you are watching this on demand, you can still use all of these features. So let's get started with today's webinar, A Case Study in Energy Storage. Today's speakers are Stuart Fox, Director of Technical Sales for CivicSolar, and Richard Riley, Power Engineer with GS Battery. Today, we'll learn about a 200 kilowatt, 400 kilowatt hour solar and storage project in St. Croix that was installed last year. And now, I'll turn things over to Stuart to get us started.
All right, thank you, Kelly. How I wanted to start out today was to kind of work up to how we got to this project and what key factors we looked at in developing it. So what we're going to do is we're going to look at a couple other projects that really led up to this commercial microgrid. Also working with GS Battery. We're just going to focus on one type of battery chemistry today, specifically the GS Battery SR1000. And whenever we look at a energy storage project, there are about 8 bullet points that we look at. I'm going to focus mostly on 4 of those critical bullet points today, and show some examples of specific examples of how they really affected a project and how they guided and acted specifically in some projects. The 8 bullet points are not they're not set in stone, but they are, I think, and they can change slightly depending on who you're talking to, what kind of project developer or designer. The bullet points are essentially, what is the source of the project? Is it an RFI? Is it a new developer that you've never worked with before? Is it a trusted installer that you've worked with on many projects? For most modern or evolving energy storage projects out there now, we're seeing a lot of new products, and we're having to put those projects together in very complex ways, and ways that they may have never been put together before. And so each of these bullet points is critical in trying to take some of the complexity and challenges out of building these things. So the source of the project, as you can imagine, really comes into play because you want to be working with with a team, and you want to be working with a trusted source of that project, because you'll see things can get very complicated. Then the use case of the project is really the second thing we look at. The use case refers to how that stored energy is going to be used. Today, the 3 projects we're going to look at are entirely off-grid. Now, in the next slide we're going to look at, it's a quick introduction to the Rocky Mountain Institute in Colorado. They have done some amazing work on categorizing and investigating and really quantifying how energy storage is affecting how solar energy is used, and how it's and affecting how people even use electricity and plan for using electricity. When we see the next slide, you'll see some use cases. The use cases we'll see on the next slide are all referred to grid tied scenarios for the most part, as far as the end user is concerned, but it's a absolutely required reading, some of the Rocky Mountain Institute reports. if you're serious about going deeper into energy storage, especially grid-side services. So the first and most important bullet point, sorry, the third on the list here, but I think the most important one is the sequence of operations. Again, we're going to have a slide dedicated to this. We'll drill down on it a little bit more, but the sequence of operations is essentially a contract between the designer, the builder, and the end user on how the system's gonna work. You know, what it's expected to do on a daily basis, what it's not expected to do, and by developing this essentially a script or a contract, it's the best way to get to the point where everybody understands and agrees on what the thing is supposed to do when the switches are all turned on. Financial model, of course, comes into play in any project. We're not going to really look at the financial model here. It's highly influenced by the use case. There's lots of wonderful tools out there for investigating the financial model. Energy Toolbase, Homer Energy are two examples that people are probably very familiar with, and there's lots of new ones evolving all the time. But we're looking at this more from a technical standpoint today. The project-specific requirements are those things that really start to winnow down the available equipment. You know, grid frequency, environmental ratings, temperature requirements, wind loading, all kinds of very site-specific physical, I would almost say physical and technical requirements of the equipment. And then the sixth bullet point here, probably I would say the second most important of all the bullet points, that's the project management. It kind of speaks for itself. Having one person or team come in and own the project from the beginning to the end is hugely important. There are so many logistics to consider and so many parties that come to the table to work on these projects, many different time zones involved, that project management is super critical. Then, of course, there's the construction phase. I think most of these attendees are well aware of how construction evolves. We're not gonna focus on that too much today. Finally, O&M. When you turn on an energy project and you've got a sequence of operations that you've built it to, there is a period of time, it could be a week, it could be a year, where the system settles into its operating environment. And it's really critical to have people available who understand it, and whether they're on site or remote, to get into the site, to make the adjustments, to fine-tune the operating parameters, to get through that critical first year. So a lot of times with a solar PV project, simple grid-tied project, you turn on the switch, you pass your inspection, and it'll run unattended for, 10, 15 years or more. With energy storage, it's a lot more complicated, and there's a turn-on process that can take several weeks to even months to get dialed in perfectly. So with that being said, thanks again everybody for joining, and we'll go to the next slide, which is just a quick introduction to the case for storage. I wanted everyone to be aware of the Rocky Mountain Institute. Again, this is for all the folks on the call who are very interested in grid-tied and grid-side services. The Rocky Mountain Institute does a really good job at breaking down energy storage services into the ISO level, the utility level, and of course, customer services. We're looking entirely at customer services today in some ways because The sequence of operations that we've built for these projects is all about either managing local demand, self-consumption, managing the time of use, and whether it's grid-tied or off-grid, these are the critical points of every energy storage project, and building them up into a serviceable and reliable sequence of operations. So that being said, and one thing I wanted to mention, if any questions come up, please be entering them into there's a Q&A window. Again, I just want to reiterate that, and we'll have time at the end to answer questions, but please feel free to answer questions as we go along. Ask questions as we go along. So the sequence of operations is, when we think about energy storage, a lot of times we just think about, what is the peak demand in kilowatts? What is the average demand in kilowatts? What is the average kilowatt hour per consumption? Sometimes we think of it in terms of seasonality, like winter versus summer. And in very small energy storage projects, like an off-grid house, or maybe a small telecom site, this can be enough to simply oversize a system a little bit or right-size the system and have it operate perfectly effectively. But when we get into commercial systems, it can get very complicated, and we put a couple examples in here. Sometimes you'll just think, well, there's loads we have to deal with. There are seasonal energy availability issues we have to deal with. But in writing the sequence of operations, everybody comes to the table and has to really state what their energy demands are. And in that period, a lot of things come up that I, for one, might not have thought of in the past, like when the system is in island mode, so to speak. There could be multiple devices that are controlling what is the actual grid signal. One device or one master device has to create the reference voltage and the reference frequency. And in a microgrid, that can either be the generator or the battery inverter. In some cases, it could be a battery solar multi-port inverter, which we'll see in a couple of these projects. But there is a very complicated handoff process that has to happen as those two devices or more have to take that leading role. Sometimes when we build with mechanical generation as well, there might be 2 or 3 mechanical generators that also have to be managed separately with a generator controller. So that also has to be brought into the sequence of operations. There might be a completely separate system. In this case, here's an example, is a fire pump. And the fire pump might have its own very specific requirements, and driven by the local authorities having jurisdiction, driven by the architect, where we're developing a project and we're thinking about how energy is produced and consumed, but then there's a superseding authority that can step in and say, hey, there's a fire, we take all control, and we have to be able to control all these devices. So that's something that also can come up in developing the sequence of operations. Finally, one more thing here. We think of these things all as closed systems, but a lot of them are highly dependent for reporting and for monitoring on outside communication. So it's important to get into the sequence of operations, any communication needs you might need. Some devices can be started from their own control panel as they come out of the box, but some of them need to have a strong and reliable internet connection. to perform firmware upgrades and to be programmed when they first come online. Obviously, if you're building a project, you don't want to show up with 4 or 5 people to start construction and programming and find out that there's no internet to the site, or or you have to rely on some sort of like a cell phone or something. So anyway, that's the sequence of operations. It's I think a critical contract or almost a recipe that gets developed for every project in the beginning phase. And so what I'm going to do now is we're going to look at 3 examples of off-grid storage project ranging in complexity from pure storage and mechanical generation to a high voltage use of, or high voltage meaning greater than 48 volts, less than 600 volt usage of lead acid battery made by GS Battery and multi-port inverters, along with mechanical generation and communications. And again, these examples are all going to be built based on advanced lead acid batteries. I'll explain why in each of these projects, but of course, your battery chemistry could be anything, and that's one of the key things that does come out or is determined during the sequence of operations. So, first project, this was purely a storage and generator project, and it's a very remote ski lodge in Alaska. It's very seasonal, so it had to be able to be turned on and turned off and managed remotely. It had to be extremely reliable. In the use case here, what filtered to the top as the key drivers was diesel fuel reduction and quiet time in the lodge. Since it's a remote lodge, obviously the people staying in it don't want to hear the background hum of a generator if they can, with the incredible open skies and silence of the Alaskan interior. So we worked with the project owners and Kachemak Electric out of Alaska to develop essentially a big stack of batteries and running in parallel with mechanical generation. And so essentially the batteries, the use case is to simply charge the batteries as efficiently as possible, conserving diesel fuel, and then as soon as the batteries reach maximum stable state of charge, to essentially coast, almost like a diesel electric submarine would. If you were trying to run a diesel submarine in stealth mode, you would want to conserve fuel and also be quiet. This is kind of the way that works. So it charges up and then discharges, charges up and discharges in a constant cycle. What that ends up looking like is a very interesting, this is a really interesting graph, I think. You'll see, this is to the upper right, you'll see a green, blue, and yellow trace. That's 3 single-phase inverters running in parallel. So this is a 3-phase service. And the inverters, you can see them moving along, handling the loads. Then this is starting from the left, obviously, is in the middle of the night when the lodge is basically asleep. Starting at 7 a.m., the inverters drop offline because the battery has reached, in this case, we had it set for 50% depth of discharge. This is when we first turned it on. We eventually moved it to closer to 70% depth of discharge. But the battery reached its maximum discharge point. The inverters drop off, and then the generator comes online, and you'll see the blue line coming up to the right where the batteries reach full charge again. And from a generator standpoint, this works really well because the generator can come to peak efficiency. So it'll ramp right up to maybe 80% of its load rating, handling the site loads, charging the battery as fast as it can, or at whatever the predetermined rate is, until the batteries reach their float voltage. And then you can see, again, the inverters start coming back online, preparing for the next day. So this was a simple use case, again, GS SLR 1000. So we are able to cycle it much deeper than a traditional lead-acid battery. Normally, we would only design on for a daily cycle if we were using a flooded battery or a high-quality AGM. Probably we wouldn't go beyond 70% or 60% state of charge on a daily basis. But with this battery, we consistently go to 50 or below, all the way down to 30% state of charge or 70% discharge. So the next project in the lineup here is stepping up quite a bit in complexity. Again, this is also a 48-volt architecture. The previous project was essentially AC coupled a generator to solar inverter. This is AC coupled, but quite a bit more complex. It's a rural hospital. So in this project, they had some reliability issues because they didn't have solar, but they had a interesting and fairly complex microgrid going using hydropower and an assortment of generators. The hospital kind of came into the limelight after the big earthquake in Haiti in 2010. This hospital was relatively undamaged and became more, it's very remote, but it became more prominent in the community and more important because a lot of other hospitals had been damaged. So a humanitarian group from the U.S. came in. They've been doing some amazing work down there, bringing in doctors, training for the hospital, and modernizing the hospital. They also brought in a group from the U.S. Southeast Smuckers Energy, a seasoned electrical construction firm, and worked with Smuckers Energy to completely redesign this as a solar microgrid. The previous project that we looked at was a good example of how a sequence of operations is established, a simple one. I think this one is a really good example of those important bullet points of project management. If you think about how difficult it can be to build a solar project with storage, there's a lot of bits and pieces, there's a lot of engineering details. This is something on the order of 100 kilowatt roughly solar project with battery storage, but it's happening 8 hours from nowhere. I mean, it's completely in one of the hardest places to get to in Haiti. Logistics are very difficult. Travel is very difficult. Communications are not too bad, but you really only have one chance to get there and build the project. And so in this case, I wanted to highlight, I think, Smuckers Energy and this project because Smuckers Energy really excelled at project management and making sure everything was ready. The sequence of operations was fully fleshed out. The engineering was fully fleshed out. And the logistics all happened to get people and materials on site to be able to build this project in a timely manner. Again, the key use case here was resilience. Obviously, it's a hospital, it's remote, power is very important, and as we all know, Haiti is often in the crosshairs of tropical storms and hurricanes. Also, what was happening is they were occasionally running out of diesel fuel and then would have a hard time making up for possible refrigeration issues and service issues waiting for diesel fuel to be resupplied. So this project was built in 2 phases. This first phase was finished at a really interesting time. So in the next slide, we will look at this is a very, I like this graph a lot because it shows how that hospital had transitioned from mechanical generation to solar with only, I think, one interesting data point. This was September 2016, just after the construction had ended. It had been running for, I think, a month and a half or so. And sure enough, here's the generator. It used to, they used to run on a couple of generators in hydropower pretty much constantly, refueling as they needed. But now we can see the generator just coming online once a day, basically for exercising. And that's great. I mean, that's exactly what you would expect if everything was done correctly from the solar and battery design. But what happens next really illustrates, I think, a good design. Getting into October, everything was still chugging along as designed up until the 3rd of October. And of course, as people may remember, that was October 2016 was when Hurricane Matthew scored a direct hit on that southern peninsula of Haiti, actually very close to, it was almost a bullseye on this project. We saw some premonitions of bad weather the day before, and then on the 4th, just lost everything, lost communications entirely. So the data that we're seeing here was being logged remotely, or sorry, locally. I didn't get to see it until I think a few weeks after the storm hit. But here's the generator. The hurricanes, when hurricanes happen, the sky just becomes completely blackened. Torrential rains, and so basically we lost solar down there. We lost the solar resource, and the generators came on as planned. Here they were running for roughly a couple of days, and then as soon as the sky cleared, boom, they dropped right out again. Solar came back online. I should add that the solar panels were very nicely installed on a concrete roof. I don't think they suffered any damage at all, other than maybe some palm fronds lying on them. And then we were back online. You see a little generator exercise. The scale is slightly off compared to the previous slide. You'll see the energy peak for the exercising is looks a little bit taller here, but here we are back to normal by the 8th. There's the little generator blip as it comes on. So anyway, that was this. That was the 48-volt microgrid, 48-volt architecture, and example of excellent project management. That other critical bullet point. One other thing. This came into discussion a little bit. Project-specific requirements did come into play here. This was originally designed for lithium. We were looking at lithium with Smucker's Energy. Lithium has a lot of incredible qualities, but we just weren't there yet as far as I think reliability and cost. And one other interesting thing that came up in conversation was lithium is not quite as recyclable as lead acid is at this point. There's no secondary market really for depleted lithium iron phosphate, for instance. So another advantage to the lead acid chemistry here was that when this battery does need replacing several years down the road, it's a very valuable commodity, and it's very likely to be brought back for recycling versus just ending up in a landfill. So that was another interesting benefit. So quickly moving on here, here's our next project and kind of the highlight of this deck and discussion. This is really important. The important bullet points here are the sequence of operations and ongoing operations and management on a local basis. This is a purely commercial project. I'm not going to go into the financials here, but U.S. Virgin Islands have very high electricity rates. This is a modern, brand new, very luxurious and very supported by the community multiplex theater. It's a big part of the social scene in St. Croix, all first-run movies, and it operates every day. And you can imagine the HVAC, communications, and projection requirements and loads are critical for this to operate efficiently and reliably. And so in St. Croix, as in many places in the Caribbean with high electricity costs, it can be cost-effective just to run on diesel. But in this case, the design was a very experienced local installer construction company called Energy-Wise Strategies, which develops projects all over the Caribbean, mostly commercial, very successful with grid-tied solar. This was moving in the direction of completely off-grid commercial endeavor, where the use cases focused on cost reduction, diesel fuel reduction, and of course resilience. And so the overall architecture for this ended up being 3 big Caterpillar diesel generators, multi-port DC-coupled inverters, so that the PV and the battery were both brought into string inverters with multiple ports. So you have a 600-volt battery bus, 600-volt PV bus, and everything is processed and then controlled by a site controller. And the big difference here between this one and the previous two is that this is where a true energy management system comes into play and has to be developed. Multi-port inverters, battery BMS, and diesel generator controllers, they all have tightly defined operating parameters, but they are essentially independent devices, and they have to be managed by a site controller. So in this case, the site controller was developed by a company called ELM. It's a ruggedized single board computer, and on that computer is the sequence of operations. In this case, is turned into essentially a software script, and then once the sequence of operations is finalized, that turned into a software script. It's uploaded onto this computer, and it's run entirely locally to manage this complex energy system. The diesel generators, of course, they have their own operating parameters. They are essentially autonomous. Their controller just determines which generator runs on a daily basis, but they are called into play by the energy management system, and the energy management system also determines when a generator might form the grid versus the solar inverter forming the grid. Then this is an interesting slide right here. This is in construction, obviously, a lot of loose wires here. But what's important for the battery, from a battery standpoint, a lot of people in this, a lot of attendees here are familiar with lithium batteries and how every lithium battery has a BMS. This is a very large, essentially 2-volt based battery running at about 500 volts. And it also has to have a BMS, which monitors every single cell, just like a lithium battery, lithium BMS monitors every single cell. And so what we needed to do here was we wanted to create a firewall that determined the battery state of health and battery state of charge and had the final say on when and if the battery could be connected and what the battery state of charge was. Then once we determined and came up with the final design for that, we were able to turn that over to the energy management system, which could then reliably call on that battery to charge or discharge based on its own calculated state of charge. And again, this is how the battery is viewed from within that BMS. So the BMS makes the call every single day as to the battery state of health and when it can be used. So going back to the original sequence of operations or key bullet points. So the sequence of operations there was very important. And then in all of these projects, this is another very important thing to consider is, since these are systems, they're very complex systems, operations and maintenance become very important. Because if you are, if anything needs adjusting or fine-tuning in the field, you want to have people who are familiar with the system before, before you need them. So what we've been doing fairly successfully is, here's an example. This was in St. Croix. St. Croix happens to have actually a lot of great, highly skilled electricians. By bringing in equipment specialists from outside and construction specialists from inside the community, we're able to create a nice sort of chain of command and ability to service the products on an ongoing basis by bringing people up to speed on this technology. And that worked out really well on an ongoing basis. So far, this has all been really about the projects. Again, these were all projects done with the GS battery SLR 1000. It's a nano-carbon battery. I wanted to introduce Richard Riley now. He's here from GS. He's just going to go over and introduce a few key bullet points and capabilities of this battery. Of course, again, anybody has any questions, please feel free to put them in the Q&A window. So Richard, do you want to introduce the battery a little bit more?
Sure. I'll introduce myself first. I'm Richard Riley, Applications and Power Engineer for GS Battery USA Incorporated. I handle supporting cells for the advanced carbon battery family and lithium battery families for sale in North American, Caribbean, Central and South American markets. Specifically to the SLR family and then the SLR 1000, I think everyone is familiar with that depth of discharge affects the battery performance and battery life. So with that said, the nanocarbon battery has a near linear performance across depth of discharge. If you take it to 70% depth of discharge, you can expect to see 5,000 cycles across that battery life. And if you only take it to 50% depth of discharge, you can expect to see 5,500 cycles. So you can see there that it's a pretty linear battery life based on depth of discharge, and that's all due to the nanocarbon enhancement of the battery. This is all backed up by IEC 61427 testing. This is a test to simulate battery performance in a PV combined application. So all systems are never going to experience, at least with the battery, are not going to experience the same depths of discharge or even recharge. So this test tries to simulate what the battery may experience in the application. I can briefly explain what the test does. So it holds the battery temperature at a nominal 40 degrees C. It will take the battery to a shallow cycle charging profile, which is you've recharged the battery, you discharge 3 hours, recharge 49 times. Then a second phase would be a high state of charge cycling, which is you discharge to a much higher state of charge 100 times. And then that is supposed to simulate 1 year of performance in a PV energy storage application. And so currently our battery is still in this testing, but it has already completed 13 cycles, which is equivalent to 13 years in a PV plus energy storage application. So a little more detail about the nanocarbon. Hopefully everyone is familiar with what takes the battery life out of a VRLA battery or any lead acid battery is the buildup of sulfation. The nanocarbon enhancement or additive to the negative plate paste creates a barrier against the sulfation crystals from growing to a size that they cannot dissolve. So illustrated simply here on the right of the slide, the orange is representative of the sulfation crystals in a standard VRLA battery, and below it you have the green geometric shape representing the nanocarbons filling up the space and preventing the sulfation crystals from growing to a substantial size, therefore allowing the sulfation crystals to dissolve every time you go through a recharge cycle. I think I can read the bullet points to you, but sulfation is a top failure mode of VRLA batteries, causing an increase in internal resistance and inhibiting the charge acceptance. That's all correlating back to the buildup of sulfation crystals over the life of the battery. The nanocarbon additive really mitigates that sulfation crystal problem altogether.
Great. Yeah, it's been a great battery to work with on these projects.
Yep. So if you have any other questions related to the chemistry and how its performance is, we have more data that we're allowed to share. I can even express just in thought, the battery can actually experience much harsher conditions than we sell it under. So in the future, I expect that we'll go beyond 70% depth of discharge and even greater cycle counts.
Yeah, for us as a designer, what's been great about this battery is it's got the physical, basically the physical format of a traditional AGM, which we've used a lot in telecom, but it has performance characteristics more on the order of a lithium iron phosphate. So it's been in this, we're not so much anymore. I think we're transitioning to being able to find some more reliable lithium products for when physical battery constraints are a lot tighter as far as weight and size. But this battery has had a tremendous advantage for us as far as reliability and overall cost advantages. So we're really looking forward to doing more projects with this in the future. But I think this gets us to the end of the presentation. I think as far as the projects and the battery, we have some time now for some questions. Let's go. Kelly, is this a good time to go to questions?
Yeah, this will work great.
Okay.
Everyone, just remember you can continue to submit questions at the bottom in the Q&A widget at any time. So let's start with.
Okay, yeah, it looks like it looks like one or two might have been answered already, but yeah, let's go.
Yeah. Okay. Yeah. So how do you get replacement parts to these remote locations?
Oh yeah, well this is something we actually get asked quite a bit. From an inverter standpoint, it actually is using these three projects as an example. We're almost entirely focused on the string inverter topology. So the first two projects were traditional battery inverters in the 6 kilowatt size range. Both of them three-phase configuration. So, and we chose that actually in the sequence of operations design and project-specific requirements design for resilience. By having multiple of the same units, we have backup communications cards, we have backup inverters, we can take one string of inverters offline, we can reassign other inverters as the master versus the slave, and that allows us a lot of reliability, and buys us time to get replacement parts shipped to these remote locations. On the battery side, what's really interesting, the battery cells are all 2 volts. And we actually had a different project in Ecuador. One of the projects got dropped, one of the batteries got dropped, the casing was cracked. It was going to take a month to get a replacement battery cell to this very remote location. All we had to do was jump past that battery in the battery string and reassign or reprogram the charge algorithm of the inverter to remove 2 volts, and everything ran perfectly. And that was a great, very nice feature of using this GS 2 volt cell. That's a good example I can think of.
Okay, perfect. Did CivicSolar offer any design services for these highlighted projects?
Oh yes, all of them. Yes, and in fact, one thing I wanted to point out, we try to set aside some bandwidth in our engineering team to help kickstart anything that's a nonprofit or a humanitarian angle. We actually do reserve bandwidth for the preliminary designs. If anybody, any attendees have projects along those lines and wants to send us a couple bullet points on what they're trying to achieve, as we have bandwidth, we do offer free pro bono design services to kind of help get those kick-started. Sometimes they just need some product selection and some block diagrams to really help them get funding. And on top of that, of course, we do offer any type of engineering, full system engineering, sequence of operations. We work with energy management service providers, and we build full plan sets as well.
Okay, on the nano-carbon battery slide, what were the green symbols on the nano-carbon battery?
Oh, yes. Well, I think Richard answered that. Yeah, go ahead, Richard.
Yeah, I mean, I can just restate it. The top slide with the orange shapes were to illustrate sulfation crystals, and the gray would represent the lead particulates of the battery. And then below it in the bottom pictogram is the same orange would represent the sulfation crystals, but then I added the green to represent the nanocarbon aspect of the battery.
Okay.
Yeah, God, that's a good graphic. I saw another one here. I can answer a couple, I think, fairly quickly. One question was, what would happen if we added wind turbines to any of these projects? And the answer is it can easily be done. A wind turbine just becomes another client, so to speak, in the sequence of operations. A wind turbine could be AC, it could be DC, and in the case of, let's say, the St. Croix commercial project, the wind turbine would be managed specifically by the energy management system. So it would actually be networked on the Modbus, local Modbus network, and controlled just like an inverter. On one of the other projects, similar to hydropower, the wind turbine might just be feeding into the DC grid. Since the batteries are all monitored via shunt, there can be multiple devices which are feeding into the DC bus, and that's how wind turbines would work with one of these projects. I think I saw another one about somebody had a question about inspectors and AHJs. This is actually something that comes up a lot. When you're building a project like this, it's a complicated project. You don't want to get too far down the development process without consulting the local authorities. It really, in almost every case that we've been involved in, the local authorities are very excited to be involved in that product development. Sure, they will bring in requirements that aren't nice to deal with sometimes, but it's much better to get those issues brought up early in the project versus when you're trying to turn it on, because once everything is shipped and installed, it can be very hard to shift directions and to convince them that you've done the right thing. So I bring in the local AHJ as early as possible is highly recommended. I saw another one here. Oh, go ahead, Richard.
I have a question regarding the discharge C rate and charge C rate. I can answer quickly. Okay. So maximum discharges are going to be 6C for 5 seconds, 3C for 1 minute, and then on our typical 48-volt system, we actually implemented a 250 amp circuit breaker, so that's going to limit the string. For the cell itself, I think the max is going to be around 1C, depending on your string. And then the charge rate, the charge C rate is always 0.2, so maximum 200 amps.
And I think you have pretty good documentation on that too. There was another one here that, correct me if I'm wrong, but this nanocarbon material is not 100% recyclable, but it's as recyclable as a standard lead acid battery. Is that correct?
Yes, that's our understanding as well. Is that
so you could
it's nearly 100% recyclable minus the casing.
Yes. Right. let's see, what else do we have here? So we got the discharge rate.
Could you maybe talk about what's the typical ROI for a project like the cinema project?
Sure. Well, that, I mean, you know, again, I didn't want to go too much into financials in this presentation, but, you know, let's say like a high level, you know, you could be spending 35 cents a kilowatt hour for grid power in St. Croix, for instance. Okay, let's say that it was 35 cents a kilowatt hour. I think it's possible to run with efficient diesels at 22 cents a kilowatt hour. You know, adding solar to that mix, you know, we can push well below 22 cents a kilowatt hour. But the critical thing about, you know, the ROI in these projects is really about the resiliency. You know, I mean, it doesn't matter what you're paying for electricity if that electricity isn't there. And so in all of these cases, it was really more about, you know, overall site sustainability from a resources and resilience standpoint. Oh, I saw another. Here's another good one, actually. Are your products listed as an assembly? So this is very important. Also references back to, for instance, the local authorities. Almost none of these projects being built are listed as an assembly. They are all made of UL listed components, but the authorities having jurisdiction can actually come in and really give you a hard time about, you know, your products, your project not being listed as an assembly. I believe, you know, Richard, you can correct me on this. I think GS is moving in the direction of a racked battery assembly, which is fully listed. You know, yes. Yeah, when we do a project, yeah, we use UL listed components, but sometimes what you have to do for a project this size is you have to have a recognized testing agency come in and actually do what's called a field listing. So they'll go in, they'll inventory everything. They have very specific engineering requirements which they have to go through, and they'll write an analysis, and they'll either pass or fail you. If you pass, they actually have a little label that they fill out and slap it onto your project, and you're officially field listed. If you fail, they give you, you know, they give you specific requirements you have to meet. You have to make those modifications, and they come in and then they'll field list you after that. So that was the answer to that question.
I can speak a little further to it, just from the standpoint of GS battery. We are taking that 48-volt rack that you can see on slide 9, incorporating a BMS that gets us through UL 1979 certification. And then that will go to sites, and then CSA will perform field inspections as well to say, yes, you're meeting, you're compliant to the standard.
Oh, great. That's huge.
All right, guys, you want to pick one last question? We're running into our hour mark.
Sure. Let me try to find a good one here. Okay, here's one I want to just reiterate. This is a good one. Who is typically responsible for programming the site controller? This is so important because the person who programs the site controller might be an expert in site controller programming, but they might live in an entirely different part of the world. So it's very important to, in a complex project like this, to bring in somebody local as soon as possible and have them involved in programming the site controller, or at the very least, training them in how to make modifications on the fly, because there's always going to be some detail that could be tweaked. Somebody might bring in a new piece of equipment, or there might be some new demand on the site, and it's really important to have somebody who has at least read the manual for the equipment and can go in and make those changes. Of course, a very valid backup to that, in the case of an energy management system, an advanced one like the ELM one on St. Croix, is it can be flashed with new firmware remotely, new software remotely. So if the sequence of operations happens to change, the engineers can upload firmware remotely. So again, it depends on the site architecture and equipment. And I think that's it. We're out of time.
All right, yeah, thanks, Stuart, and thanks, Richard, for answering some of those questions. If you did submit a question and it was unanswered, please feel free to reach out to our presenters on our own. And again, this webinar will be shared with all registrants so you can view it again at your convenience. So thanks again to CivicSolar for sponsoring today's webinar. And thanks to everyone in our audience for participating. Hope you enjoyed our presentation, and we invite you to join us for more Solar Power World webinars in the future. Thank you.